Hello. Uh, so in this video, we'll discuss the backtracking. In this first video, I'll just introduce the technique of backtracking. So this kind of puzzle you might have played several times in your childhood, right? So when you want to draw a path from source to destination, in the very first attempt, you will never get a correct path from the source to destination. You might have so many times gone back and then taken another path. So the same thing is applicable in the coding of backtracking too. This is one more algorithm design technique. So backtracking technique is used in so many problems. It has so many applications, like how we use greedy and dynamic programming for solving the optimization problems. We'll solve backtracking also for the same kind. And not only for that, for the problems, for any problem you need solutions which satisfy the given constraints. There also you can use. So constraint satisfaction problem, robotics, artificial intelligence, network communication, designing games which involve solving puzzles, Sudoku, all those things we'll be using backtracking technique. It has so many applications. So coming to the introduction, generally we use backtracking when the solution of a problem is expressed as a tuple. So a tuple of n values. Those n values look in this way: x1, x2, so on up to xn. The tuple size can be 4 values, 5 values, 10 values. So it's a variable length size tuple based on the problem you are solving. Okay. So based on what you are solving, this tuple may contain unique number as the numbers may repeat. It definitely depends. It's completely dependent upon the problem we are going to solve. And so when we use this backtracking, when we already have greedy and dynamic programming for solving the optimization problem, when do we go for backtracking? So for any problem, if you are able to devise a recursive kind of solution, we can go to backtracking. And another thing is, if that problem is having more than one solution, uh, then also you can go for backtracking. That means the problem is having a set of solutions, then we can go for backtracking. And you want all those solutions which satisfy the constraints. At those times also we can go for backtracking. The answer is expressed as a tuple of n numbers like this, and sometimes the tuple may have to minimize or maximize the objective function, like the object will have optimization functions, no, in that way. For example, suppose in your problem they were asked you for a solution which has four numbers, which can have four numbers, and the allowed numbers are either 0 or 1. So then the answer tuple may look in this way: what are the various possible alternatives you will have? Starting from 0 0 0, you can have 15 different combinations of outputs. The various permutations and combinations you can generate with the constraints that the tuple size is 4 and the allowed numbers are 0 and 1. At those times, the number of permissible answers are 15. Okay, checking for all the 15 permutations and giving the desired solutions is referred as brute force technique. But unfortunately, the brute force technique may take a lot of time. One thing to remember is brute force technique may take time, but it always results for the best solution, but not suitable for the biggest problems. It is suitable only for the smallest problems. Okay, so brute force approach means for all the n tuples, evaluate them with the objective, and whatever is giving the maximum or minimum value, that you will store as answer, but it takes a lot of time. But the backtracking technique obtains the same answer with less number of trials. So here the main idea of backtracking is, here we understood that the answer comes in the form of a tuple. At every step you will be constructing, you will be deciding only one value, next value, next value, so on in that way. While taking decision for one value, if you identify that this combination of values are not leading to the answer, you can stop constructing the rest of the tuple, go back and take another number for that particular one. That is the basic idea. So basic idea is we'll be building the solution vector one component at a time, and we'll use the criteria function. Criteria function means for every problem we'll be having set of rules. No, we'll apply those rules and we'll check whether that set of solution is leading us to the answer or not. So we'll check the criteria function, and if it is good answer, we'll move forward, otherwise we'll stop there and go back. That is the basic idea. And what's the main advantage if I use this idea means, after I construct half of the answer, the partial tuple, if it is not leading to the solution, then the remaining tuple xi plus 1 to xn can be ignored. There is no need to construct and check, right? That's the main advantage. So till now, for all the problems we have seen constraints, but for backtracking we'll be having two kinds of constraints, guys. They are explicit constraints and implicit constraints. Constraints are rules that we need to satisfy to form the solution. Implicit constraints, as the name suggests, the rules are specified in the problem definition itself. And coming to explicit constraints, you will be coming up with some rules, and mainly those are the rules that they'll tell you about the solution vector. What is the size of the solution vector? What values are allowed in the solution vector? Generally, those you have to devise as a coder after understanding the problem. Those are referred as explicit constraint. What is the main idea, main advantage, and about constraints is specified here. And let me show an example for explicit constraint. See, if answer tuple can contain all positive numbers, then any positive number is allowed in the answer tuple, then I can write in this way. If the answer tuple allows either 0 or 1, then we can write in this way. Or the answer tuple allows numbers from 18 to 21, like that, in the range of values, then you can write in this way. Okay, so uh, all the tuples which satisfy the explicit constraints are called as solution space. Here in this case, all these 15 tuples are referred as solution space. Among these solution space, we have only two final answers, not two, we'll have only few final answers which satisfy the implicit constraints also. Okay, so all the tuples which satisfy the explicit constraints means what is the size of the vector, what are allowed in the vector. So what if they satisfy explicit constraints, we'll call it as solution space. In that solution space, we'll be having few 0 or 1 or more than 1 final answers, best answers. Okay, so for this solution space, we'll be constructing a tree soon. That tree is referred as state space tree. In that tree, we'll do search algorithms to search for the answer. So solution space, all tuples that satisfy the explicit constraints define a possible solution space for the problem instance. Implicit constraints means they are specified in the problem itself. They define how to construct this tuple and all. Okay. To explain backtracking, one of the first example we can take is n queens problem. Here it is given as 8 queens problem. That means the n value is 8. Whatever it may be, the queens problem is in n queens problem, you have to place n queens in an n cross n chessboard in such a way that no two queens should attack. Attack means, let me write here. If I place one queen here, no two queens should be in the same row. No two queens should be in the same column. and no two queens should be placed in the same diagonal. No two of them are in the same row, column or diagonal. Okay, and as you have to place n queens, the answer is an n tuple. Suppose if you have to place 4 queens in the board, answer is a 4 tuple. If you want to place 8 queens on a board, answer is an 8 tuple. So the answer will look in this way. X1, X2, X3, so on up to X8. Here, while constructing the answer, we'll assume that every queen is placed in one row. So the first queen is placed in row 1, column X1. Second queen is placed in row 2, column X2. Row 3, column X3. Row 8, column X8, in that way. Okay. So we will be constructing one answer at a time, and when I take a decision here, no, I should not place in that way, then I'll take another decision. In that way, we'll be constructing the final vector. Here, what are the implicit constraints specified in the problem? Place 8 queens and they should not attack. And explicit constraints are the tuple size is 8 and the numbers you can place here are from 1 to 8. Column numbers are from 1 to 8 and the column numbers should not be repeated. Those are explicit constraints. Okay. Sometimes you will be asked define n queens problem, define 4 queens problem and define 8 queens problem. This is definition of 8 queens problem. Based on the problem you need to write implicit and explicit constraints. Based on this definition you can come up with a definition for 4 queens and n queens too. Okay, this problem can be easily solved with backtracking. Let me show how. So earlier at the introduction slides I have shown you that there is solution space. That means all the permutations of the explicit constraints, a tuple which satisfies the explicit constraint, all those tuples are referred as solution space. So we will be drawing a solution space as in the form of a tree. That tree is referred as state space tree. Suppose if I take a 4 queens problem, we have to come up with 4 numbers. What is the location for the first queen, which column, location for the second queen, location for the third queen, location for the fourth queen, in that way. Okay, so what explicit constraints are saying? The size of the tuple are 4 and numbers from 1 to 4 are repeated. Those are explicit constraints. Implicit constraints are saying that in the same column no two queens and the same diagonal no two queens. So we'll keep it aside. First we will understand the answers which satisfy the explicit constraints. That means so this is one answer, this is another answer, this may be another answer, this is another answer. In that way we can generate n number of permutations, nearly 4 factorial permutations. We'll see them. See, when the first queen is placed in the column 1, we have space for the second queen in second, third and fourth columns. Okay, so in column 1 queen 1, column 2 queen 2, column 3 queen 3, column 4 queen 4. In that way 1 2 3 4 is another one alternative and the next alternative is 1 2 4 3. So how this tree is drawn we'll see. So when the first queen x1 is 1, we have to take decision for x2. So for that it can be 2 3 4. Let us move in this path and when it is 2, for the third queen I left with the choices 3 and 4. When I place the third queen on the third column, I left with a choice for the fourth queen for 4. Okay, So this is one alternative. Let us see another alternative. Third queen can be placed on the fourth column. Then the fourth queen can be placed in third column. In that way we have nearly 24 permutations for this. All these solution space is specifying answers which satisfy the explicit constraints. Among these 24 tuples, we have only few tuples which satisfy implicit also. They are called as answer states. We need to identify them. Okay. And coming to the numbers in the node, this numbering is followed by DFS. You might have gone through DFS and BFS techniques in your second year. So every searching in the tree or a graph starts from the root node. So root node has 1, and uh, visiting children of the node are referred as exploring the node. Once when we explore this node, first child is visited. So when the first child is visited, it stopped the exploring of the remaining children and it started exploring the node 2. So that's the reason number 2 is given to this. So it has 3 children, started exploring. So it has seen that it has visited the first child. It stopped exploring the remaining child. So the node number 3. Again it went to its children, node number 4, 5. Then it started visiting the next child of this, 6, 7. It went back, again backtrack. Then it has seen no more children. So backtrack, it went here. Yes, it has one more children. So the next node number is assigned to this. In this way, DFS search happens, right? So if I search for solutions in this state space tree using this DFS technique, we call it as backtracking. In the same tree, if I use BFS technique, then we use that algorithm design technique as branch and bound. Okay. For now, on this tree, we will be using DFS technique to search for the answers. Let me introduce few more words here, guys. So I started at root and we started to explore this node. So when I am exploring this node is called as E node. So I have visited node 2 and left these 3 nodes and started visiting this node. Now this node becomes the E node. Again, means for which node we are generating the children, that node is referred as E node. Again, this node is generated, this node is referred as E node. Okay. And after visiting all its children, we are going here. That means there are no more children for 3 when I went to 8. So then it becomes the dead node. Okay. When I am doing all this, the node 1, 2, they're still having life. They are not dead. Okay. So these nodes are called as live nodes. At any point of time, we'll have only one E node. We may have one or more live nodes, one or more dead nodes. But at any point of time, we'll be having only one E node in the tree. So let us understand how to search for a solution for the 4 queen problem. So assume that this is your board, 4x4 board, and I'm starting from here. Okay, and I'm taking decision for my x1. I want to put my queen 1 here, so queen 1 here, and then I came here. So I again doing DFS. So queen 2 I want to put here in the second one. So if I put queen 2 here, it is coming in the same diagonal. So I should not go here and backtrack. I will take another decision and I'll try to put queen 2 here. So if I put queen 2 in the third column, it's okay. They are not in the same column, they are not in the diagonal, so I can move further. 1 and 3 are utilized. Now I'll take decision for the third queen. If I put it in 2, no, I should not put it in 2, third row, second column, because they are becoming diagonal. So I'll go back. I'll try to put it in fourth one. If I put here also, then also it is diagonal. So I'll go back and I'll backtrack. uh, do you have one more solution? It says you can put it in fourth column. 1 and 4 not diagonal, so we'll use 2. When we use 2, 1 4 2, it says okay. So then I can move here, and if I put the fourth queen on third, 2 and 3 becomes the diagonal, so I can't put here. So I'll go backtrack and come here, and I'll try to put it in the third column. It says 4 and 3 diagonal. Backtrack. If we backtrack, will come here. If we backtrack, will come here. Whenever we backtrack, we have to check, is there any possible choice for the second queen? I check it, second location, third column, fourth column, all columns are gone. No, I don't have any alternative left. So I can go here. Try to put the first column in the second column, first queen in the second column. Then I left with, then I can use 1. It says no, diagonal. If I put in third column, it says no, 2 and 3 are diagonal. Then what is the other alternative? I can put in fourth column. Yes, it's good. If I put in fourth column, the other choice is I can put it in third column. No, 3 and 4 will become diagonal. It says you put it in first. Yes, it's okay. You can put it in first because 4 and 1 are not diagonal. Then I have to check the alternative for the fourth queen. 2 4 1 are utilized, so fourth queen can be placed on the third. Yes, it's good. So this tuple 2 4 1 3 is an answer. 2 4 1 3 is an answer. We'll see whether it is or not. 2 4 1 3. Yeah, all the 4 queens are placed in the board, and no 2 queens attack with this solution. Okay, have you seen the advantage of this? I am searching in the tree, but I am not checking all the paths in the tree. Whenever the solution is not leading to the final answer, I am pruning that path and going back. Okay, that means after generating every possible xi and checking a condition, that condition is called as backtracking. So whenever you found some answer, you should not stop it. You have to check for the other alternatives also. You complete this tree for 3 and 4, you will get one more answer, guys. Okay, so you will be asked to draw these kind of state space trees also in the examination. So hope this is clear to you. So some terminology, all the solutions are referred as solution space, and only few of them are answer states which satisfy both explicit and implicit. The tuples which satisfy explicit are called solution states. The tuples which satisfy both explicit and implicit are referred as answer states. And this entire tree organization of the solution states is referred as state space tree. In that tree only you will be doing searching. If you use DFS on that tree, it is backtracking. If you use BFS on that tree, it is called branch and bound. Okay, and these trees can be sometimes static, sometimes dynamic. If the tree organization is not dependent on the input, then we call it as static. Otherwise, we call it as dynamic. Okay, and what is live node, what is E node, what is dead node, what is bounding function, I have conveyed you. And bounding function means at every point of time you will be checking one condition to check or to kill the path. Okay, when we solve problems and write algorithms, we will see how bounding functions are applied. Okay, so how the general method for backtracking is, first we have to we know from the constraints we will be knowing what is the size of the answer vector. So for now, assume that some of the answers are calculated x1, x2, xi up to the ith value it is calculated, and to find out I plus 1th value, you will be using all these previously calculated values, and you will see with the help of previously calculated values, can I put this value in the I plus 1th location or not. After identifying I plus 1th location's value, you will check the bounding condition. See, for the second queen, if the first queen is placed in first column, for the second queen I am using either 2 or 3 or 4. That means previous x1, x2, xi are helping me to decide I plus 1. Okay, after I take up a value for the I plus 1, I'll apply one condition. I'll check if I put this value in I plus 1, is it going in a proper way or not. If it is not, I'll prune the path, otherwise I'll move forward. This is the general formulation. So to decide the k value, we'll check with the help of the previous k minus values. We'll check, take up one value and check the bounding function. If it is leading to the answer, you will write the answer, and you'll move the path to find the k plus 1th. That is the general method for the backtracking. Okay, so this is recursive algorithm for the backtracking. Here it is the bounding function. Here the probable values for k, and if k exists, it will move forward. If you are unable to get some value for xk, then will terminate. So you can go through this. This is an recursive algorithm for backtracking. We can also write backtracking solution with the iterative thing. So you can check that. But what factors show influence on the efficiency of the backtracking algorithm is, you need to find out a value for xk, which value is suitable for xk. So that takes some time. After that, if I take up this xk, is it satisfying the explicit constraint or not, and you need to check the bounding function. So which xk value is satisfying the bounding function. All these you need to check while writing the program. These will take the time for generating the answers. This is all about introduction to backtracking. Next we'll see the n queens problem. From the introduction to backtracking, you will be asked to write the general method, and some definitions and all are there, and state space tree construction is also important. Hope this is clear to you. Bye.